In this module, we will provide some basic knowledge on the IEC 61850 and its significance in renewable energy system security. Upon completion of this lesson, students should be able to list the core components of the IEC 61850 standard, understand the data model of distributed energy resources, understand the communication service mapping to different protocols, list the communication protocols utilized by IEC 61850 standard, and understand the vulnerability and security issues of different IEC 61850 protocols. In this section, we will investigate the IEC 61850 standard, which is predominantly used in distributed energy systems and renewable energy systems, such as those in wind and hydropower. The IEC 61850 is an international standard developed by the International Electrotechnical Commission's IEC Technical Committee 57. The initial version of IEC 61850 defined communication protocols between different equipment inside substations, such as IEDs, merging units, and protection devices. Based on the success of the IEC 61850, the standard has been expanded to cover distributed energy, wind energy, and hydroelectric power plants. The IEC 6150 standard consists of several parts. Part 1, IEC 61850-1, provides a basic introduction and overview. Part 2, IEC 61850-2, is the glossary. Part 3, IEC 61850-3, provides general requirements. Part 4, IEC 61850-4, has the system and project management. Part 5, IEC 61850-5, has communication requirements for functions and device models. And Part 6, IEC 61850-6, is the configuration description language for communication in electrical substations related to IEDs. The Part 7 component is made up of the following subcomponents. Part 7-1, IEC 61850-7-1, Basic Communication Structure of Principles and Models. Part 7-2, IEC 61850-7-2, Abstract Communication Service Interface. Part 7-3, IEC 61850-7-3, Common Data Classes. Part 7-4, IEC 61850-7-4, Compatible Logic Mode Classes and Data Classes. Part 7-410, IEC 61850-7-410, Hydroelectric Power Plants, Communication for Monitoring and Control. Part 7-420, IEC 61850-7-420, Distributed Energy Resources Logical Models. Part 7-500, Part 7-510, Part 7-520. Use of logical modes to model functions of substation automation, hydropower plant, and distributed energy resources. As we can see from the IEC 61850 parts, IEC 61850 is not only a communication protocol similar to Modbus or DNP3. In addition to the communication protocol, IEC 61850 defines data models, abstract communication service interfaces, communication protocols, and configuration language used to configure IEDs and control devices. Communications for the DER plant's operation involve two different types of communications. Local communications between DER units and the control system, and communication between the DER plant and the operators or aggregators who manage the DER plant as a virtual source of energy and or ancillary services. The IEC 61850 communications can be delimited into four parts. Number 1, information modeling, i.e. the types of data to be exchanged. Number 2, services modeling, i.e. the read, write, or other actions on the data. Number 3, communication protocols, i.e. the mapping the data types and services to actual bits and bytes. And number 4, telecommunication media such as fiber optics, radio systems, wireless systems, and other physical equipment. IEC 61850-7-420 defines information modeling for DER. IEC 61850-7-2 defines service modeling, and IEC 61850-8-1 defines communication protocols. Data information models provide standardized names and structures to the data that is exchanged among different devices and systems. The information model hierarchy from bottom up is described below. Number 1, the standard data types such as Boolean, integer, and floating point. Number 2, common attributes. attributes that can be reused by different objects, such as the quality attribute. Number 3, common data classes, CDCs, are predefined groupings building on the standard data types and predefined common attributes, such as the single point status, SPS, the measured value, MP, and the controllable double point, DPC. In essence, the CDCs are used to define the type or format of data objects. Number 4, data objects, DO. Predefined names of objects associated with one or more logical nodes. Number 5, logical nodes, LN. Predefined groupings of data objects that serve specific functions and can be used as bricks to build the complete device. Examples of LNs include MMXU node, which provides all the electrical measurements in three-phase systems such as voltage, current, watts, VARs, power factor, etc. And XBCR node for a circuit breaker with a short circuit breaking capability. Number 6, logical devices, LD. The service model composed of relevant logical nodes for providing the information needed for a particular device. Example of the logical device a circuit breaker device could be comprised of the logical nodes, circuit breaker node, XCBR, and switch controller node, CSW. A PV system consists of interconnected PV modules using combinations of parallel and series connections. PV modules are connected in series to form PV strings, and those PV strings are combined together in parallel using combiners box. A single PV array is considered to be a single DC power supply unit. Since the power system requires AC power for an interconnected generation, a power conditioning unit, PCU, or converter is required to transform the DC output of the PV array into AC. For large PV systems above 200 kilowatts, individual PV strings and equipment such as fuses are monitored. This figure shows the logical nodes and the logical devices needed to monitor and control PV systems according to IEC 61850. The system consists of a PV array connected to a DC-AC converter through a DC circuit breaker. A battery storage is connected to the DC bus of the DC-AC converter. The DC-AC converter is connected to the grid through the DER circuit breaker. Several meters are used to monitor PV power production, utility energy, and load consumption. The PV system is monitored and controlled using a DER unit controller. In the next slides, all logical nodes and logical devices will be explained in detail. The DER device controller logical device defines the operational characteristics of a single DER device, regardless of the type of generator or prime mover. The DER device can contain the following logical nodes: DRCT, DER unit controller characteristics including what type of DER, electrical characteristics, etc. DRCS, DER unit status. DRCC, the DER unit control actions. FSEQ, the sequencer status if used in startup or shutdown automated sequences. MMXU, the DER active or reactive power measurements. Circuit breakers logical nodes include the following: CSWI, switch opening and closing controller. XSWI, circuit breaker without short circuit breaking capability. XCBR, circuit breaker with short circuit breaking capability. Here are the PV logical nodes and the battery logical nodes. Note the connection of the PV logical nodes to the battery system. We now look at the IEC 61850 security and its implication to renewable energy security. The IEC 61850 maps abstracted definitions into communication protocols based on application requirements. In general, there are two different categories of applications with different timing restrictions. Real-time applications with strict time requirements such as protection, and automation and control functions with no strict time requirements. For real-time application with strict time requirements, IEC 61850 maps the abstracted definitions into two main protocols: generic object-oriented substation events, GOOS, which is used to transmit critical events data, and sampled measured values, SMV protocol, to transmit real-time measurements. Both GOOS and SMV are layer 2 protocols. For automation and control functions with no strict time requirement, IEC 61850 utilize the Manufacturing Messaging Specification MMS protocol. MMS is a layer 3 protocol. This figure shows the communication protocols utilized by the IEC 61850 standard. The SMV and GOOS are Ethernet Layer 2 multicast protocols. Layer 2 protocols provide data delivery with minimum delay, but cannot be routed. Layer 2 protocols are used in the local LAN inside the DER power plant or substation to deliver time-sensitive signals and control. MMS protocol is Layer 3 TCP/IP protocol. It can be routed to other networks. MMS is used in automation and coordination with no strict timing requirements. MMS can be used between interconnected microgrids and between microgrids and control centers. The IEC 61850 itself does not specify security measures for communication protocols. Since it utilizes TCP/IP protocols, it brings all known vulnerabilities of TCP/IP protocols to the power system control and automation. The security of Ethernet-based communication protocols utilized in power systems is defined by another standard, the IEC 62351. The source of attacks against IEC 61850 communication protocols may include an insider with access to automation and control network and who can infect the system with malware either intentionally or unintentionally via infected devices. It can also originate from a supply chain where IEDs can be infected with malware during the manufacturing or installation process. The IEC 61850 protocols can be impacted by denial of service, eavesdropping, and man-in-the-middle attacks. IEDs can be impacted by password cracking attacks to gain access to configuration and control interfaces. Since MMS utilize TCP/IP protocols, it can be impacted by address resolution protocol vulnerability called ARP cache poisoning. In this attack, the malicious device pretends to own the MAC address of the victim device by broadcasting ARP reply messages to update the ARP cache table. Once the ARP cache is updated with an incorrect MAC address, the malicious device will gain access to all data transmitted to the victim device and can perform man-in-the-middle attacks. In order to protect TCP/IP-based protocols utilized in power systems, including IEC 61850, Modbus, DNP3, and other protocols, TC57 developed the IEC 62351 security standard to define the security measures and guidelines. The objective of the IEC 62351 is to prevent eavesdropping and spoofing attacks, detect intrusions, and authenticate data transfers through digital signatures. The IEC 62351 standard requires TLS and message encryption for TCP/IP-based protocols, including MMS messages. IEC 62351 recommends not to use any encryption on Goose and SMV messages to meet the restricted response time of less than 4 microseconds. IEC 62351 recommends the use of RSA for Goose message authentication. Unfortunately, no vendor implemented the recommendation of authenticating Goose messages using RSA, which leaves the Goose and SMV unprotected. This table shows the signing and verification times using the RSA algorithm with different key lengths at different processors. Any key shorter than 1024 bits is considered too weak to protect the system. As depicted in the table, the signing and verification process takes more than 4 milliseconds, allowed by the IEC 61850 standards. Most IEDs have processors with very limited resources and processing power compared to processors in this table. As a result of this, Goose and SVM are not protected by any encryption or authentication mechanism. Several researchers studied other authentication mechanisms, such as HMAC, to authenticate Goose messages. The Goose datagram starts with the destination's Media Access Control MAC address, which is a multicast address reserved for IEC 61850 applications. It starts with 01:0C:CD, followed by 3 octets to form a 6-octet source MAC address. A Goose message is an IEEE 802.1Q Virtual Local Area Network ID, VLAN ID, and a unique Ethernet type, 88B8. The application ID, app ID, field is a 4-octet field. The length field represents the length of the overall Goose datagram minus 8 bytes and is followed by 2 reserved fields left out of the standard for future use. The Goose PDU field is composed of 12 subfields as follows. GOCB REF, Goose control block reference. Time allowed to live, the time a receiver waits before receiving a retransmitted message. DAT set, name of the data set. Go ID, ID of the publishing IED. T, the timestamp indicating a new Goose event. stnum, the counter that increments with every goose event, sqnum, the counter that increments with every repeated goose event. Test specifies a message is intended for testing. Conf REV, number of times a data set has changed. NDSCOM, needs commissioning field. Num data entries, number of data elements in all data. All data, actual data being sent, Boolean, integer, float, etc. Each goose message has a status and a sequence number field, stnum and sqnum respectively. When an event occurs, for example, an overcurrent is sensed. The IED instantly transmits a message with an incremented stnum field. The message is then repeated with variable increasing time delay until the maximum defined period is reached. The sqnum counter increments with every repeated message until the maximum number count is reached. IEC 62351-6 states that a subscriber IED should discard any message with an stnum less than or equal to the previous message in order to mitigate some cyber attacks such as replay and man in the middle. The Goose protocol is vulnerable to different types of attacks, such as data manipulation and goose poisoning attacks. In the data manipulation attack, the attacker sniffs the network communication waiting for goose message transmission. Since the goose message data is not encrypted, the attacker can receive and decode the data field to find out the data structure used by the IED. Once the data structure is known to the attacker, he can construct a new message with manipulated data and transmit it with a new status number. All subscribers will receive the message and process. Goose poisoning attack is based on the fact that the subscriber's IEDs should disregard the received message if the message number is less than the message number of the previous message. In this attack, the attacker sniffs the network, waiting for a goose message transmission. Once the message is received, the attacker can decode the message and obtain the latest number and broadcast a new message with a much higher status number. For example, if the original status number was 2, the attacker will transmit a new message with a status number equal to 10,000. When the subscribers receive this message, they will disregard all messages from the original device until the status number reaches 10,000.